Welcome to the second to last session of the conference. We will start with Pin Cheng from UMass.
Hello everyone. My name is Pin Shan Cai. I'm from UMass Amherst. I'm presenting this work on behalf of my friend Haoran Yan, who couldn't be here unfortunately. So Haoran is from the Institute of Computing Technology, Chinese Academy of Sciences. This is a collaboration work between Haoran, his supervisor, Xiaolong Jing, and other colleagues from ICT-CAS. So the presentation will include the 4 parts. The first one will be some background information and introduction about event detection task. The second is the motivation for proposing the model. The third is details about the model and multi-order graph convolution and attention aggregation. The fourth is experimental evidence about the model. And the last are conclusions and future work. So we first start from the background and introduction about event detection task. According to the definition of automatic content extraction, the event detection task is a subtask of event extraction, which aims to extract event triggers from individual sentences and further identifies event types. The event trigger is the word that most clearly expresses its occurrence. For example, in the blue sentence, the trigger word is married, which represents a merry event. We can split the existing method into sequence-based ones and dependency-based ones according to whether they use dependency trees or input sentence. At present, dependency-based methods achieve better performance than sequence-based ones, as they can better capture the keywords of candidate triggers. For example, in a given sentence, the candidate trigger fired could indicate an attack event or an end position event. The keyword distinguishes type and distinguishes type are the keywords to distinguish this type are blood and soldiers, which has fewer distance through the dependency path than sequence. In dependency-based methods, the most common way is to treat dependency tree as a graph and adopt the graph convolution network. However, these methods only use the first-order dependency relation in graph convolution. To learn high-order dependency relations, they use a stack of GCN layers to iteratively update the graph representation of each node, which will cause the over-smoothing problem. For example, since node 1 is always connected with node 2 and 4 in graph convolution procedure, this representation will be more and more similar after iteration, which damages the diversity of the representation for classification. To solve this problem, we propose a multi-order graph attention network-based method for event detection called Morgan. So Morgan utilizes both first-order and high-order dependency relation to explicitly model multi-order graph representation of candidate trigger words. It consists of 3 modules: word encoding, multi-order graph attention network, and attention aggregation. So suppose that input sentence has n words. For each word wi, we use the following lookup table features in word encoding module: word embedding, the word I, entity type embedding eti, part of speech embedding pose I, and relative position embedding psi. We concatenate these features as xi and fit it into the bidirectional LSTM, like other dependency-based methods did. So PI is the output representation of word I. Then we introduce the multi-order graph attention network module. We transform the dependency tree to first-order dependency graph, which is the green rectangle. It contains 3 subgraphs. A alone is an n by n adjacency matrix, which saves the dependency edges of the dependency tree. A ref is it saves the reverse edge of the dependency tree, so it is the transpose of A alone. A loop saves the self-loop edge for each word, so it is the identity matrix. High-order dependency graphs store multi-hop neighbor relation in the dependency tree, which have the same structure as the first-order ones and are calculated through matrix multiplication. In the illustration, the blue rectangle saves the second-order dependency graph, and the yellow rectangle saves the third-order dependency graph. The graph representation is calculated by element-wise add of graph convolution, and output of each subgraph is a different order. We adopt the graph attention network for graph convolution. So here is the detail of the graph attention, where Uij is the normalized weight of word j, which is used to calculate the graph representation of word I. So this illustration takes word 1 as an example and use the dark red edge to indicate the words interacted with word 1 at different order. As we can see that each word is at most used only once in the generation of word 1's graph representation, which avoids the occurrence of over-smoothing problem. The attention aggregation module is used to aggregate multi-order graph representation of each word I. It uses a global vector CDX to capture the importance of graph representation of each order. CDX is randomly initialized and updates through backpropagation. So this illustration takes word 1. Okay, no, not this one. Since the number of non-trigger word is much larger than the event trigger word in the dataset, we use the bias loss function, while lambda is a bias hyperparameter. So we evaluate the performance of the method on the well-known event extraction dataset, ACE 2005. This data covers 33 event types. The table above shows the table split for our experiment, and the table below is a hyperparameter we use according to the performance on the validation set. In order to validate the proposed model through experimental comparison, we chose the following typical model as the baseline. The sequence-based method contains both feature-based method and the representation-based method. The dependency-based method contains both dependency-enhanced RNN and GCN-based methods. This table presents the performance comparison between different methods, while dependency-based methods are marked with blade symbol. We can see that our proposed method, Morgan, outperforms all other existing state-of-the-art methods in terms of both precision and F1 measure, while this recall is comparable. Moreover, Morgan achieved the best performance in terms of precision, recall, F1 measure among all dependency-based methods. For ablation study, we set 3 variants of Morgan. The first one, Morgan first, only used the first order dependency graph. Morgan GCN uses GCN instead of GAT. And Morgan min adopts the min pooling for aggregation to replace the tension aggregation module. This table, sorry. Yes. I couldn't see the mouse here. This table presents the performance of different variants. Morgan first achieves the worst performance, which suggested that higher order is helpful for. We suggest that higher order logics are helpful for better performance. Model GCN also achieved better less performance than modern GAT, which suggests that GAT is a better model than GCN. So as a conclusion, this paper we proposed a multi-order graph attention network-based event detection method, Morgan, as we first applied the GAT to event detection. Through experiment, we also showed this method achieved better performance in terms of both precision and FM measure. For future work, we will try to apply Morgan method to event argument extraction task. So that'll be all for the presentation. Thanks.
Let's thank Peng-Cheng. Time for one question. Maybe 2 if it's quick.
Well, I guess if you have a question, you could have it sent to the author, although I'm not the author of this paper, so
I was going to say we should take it easy on him.
Yes.
Thank you.